Hi, everyone, and welcome to Day 2 of the Future of Electrification. As electrification progresses, more emphasis is being placed on the costs associated with moving to an electric system. Today, Marc Blindenbach, business developer for Unitial Technologies, will take you through some best practices of utilizing data to fully understand the true total cost of ownership of an electric vehicle. Remember that throughout the session, you can ask your questions via the Q&A chat, and additionally, each session will be recorded for viewing later. And with that, I'm pleased to welcome Marc.
Welcome everybody to the topic of using data to improve TCO of zero-emission construction. So my name is Marc Blindenbach. I'm business developer at Unitial Technologies. And before doing this, I had a career in developing battery systems for off-highway machinery at a company making those battery packs. I also have experience in terms of data analysis and decision making, and basically am now applying that as business developer at Unitial Technologies. The history of the company Unitial is a very brief one, but also a bit further back into the history. So there was a solar team from the University of Eindhoven that participated in a challenge in Australia to drive a specific distance with a solar-powered vehicle. The student team was about 30 people, and they had to design the machine completely from scratch. That means including the drivetrain and also the battery pack. And the focus, of course, was on winning the race, which has to do a lot with finishing first in the shortest time. But that also requires managing the energy within the machine. For example, not driving too fast, but also not driving too slow to optimize when to charge the battery and when to switch the battery, and basically including many factors that will impact the energy consumption. The proof of their capabilities was in the pudding when they won the first prize of that contest. Following that, all the members went their own direction, mainly in the high-tech industry, applying their technical skills, as well as the automotive sector. So further developing cars or trucks, and specific focus on the electrification of those. Halfway 2023, the co-founders decided that they wanted to work together again as a team. So that was a part of that solar team, and that they wanted to focus on the off-highway segment, as electrification in this segment is lagging a bit behind other markets. And there is a large potential to actually make an impact by coming up with new ways, technologies, and tools to address this market. Our focus will be on reducing the amount of diesel that is consumed in the segment. I'm going to show you a lot of pictures about construction, but that is to make it a bit more explicit. Now, if we look at the reduction of diesel, well, we do this for various reasons, right? So diesel is classified as a known carcinogen, and in the Netherlands, employers must take measures to eliminate the exposure to the diesel fumes wherever possible. And of course, an electric machine makes it possible to fully eliminate those, but there are other ways to also reduce exposure. Additionally, there's a global need to reduce the CO2 emissions and reduce the impact on the climate. And then there are a number of very interesting trends that basically impact the license to operate for diesel itself. And with that, what we mean is, right, there are clean air agreements in cities where basically they want to reduce the amount of smog. You can see this particularly in Chinese major cities. Then there's a CO2 tax within Europe, basically punishing you for emitting CO2. Then there are areas where nitrogen depositions basically are destroying natural habitats and limiting where you can actually do work. And then last but not least, there's definitely an element of noise reduction, both for the operators of machinery, but also for the environment in which the machine is used. And typically we see this quite heavily in the cities, where there is a requirement or a wish to actually reduce the amount of noise. All in all, that's quite a lot. And still, the balance is not swaying completely towards electrification. Now I will press a button so that you will see a poll. And basically the question is, what is the main reason blocking widespread adoption of electric machinery? So there's a few possibilities that you can answer here. Equipment can be too expensive, people can have no power available, maybe they cannot charge the machine where they need to work, or maybe the machine simply doesn't do the job that well. Or there could be others, of course, ones that were not listed here. So I'll give you a few more seconds to answer, then we'll close the poll and continue. Okay, so we can see a bit of a split between not having electricity, but also equipment being too expensive, and no options to actually charge the machinery, which are all, of course, extremely good reasons why that is being slowed down or delayed. Let me see. Yeah. So we think that we should look at this from a holistic point of view. In order to achieve the goal of reducing diesel consumption, we shouldn't be looking just at the machine itself, right, which is kind of like the iceberg, but also everything that comes along with it, right? The machine needs to do its work, it needs to do that at a good cost, and it needs to do that in a way that actually fits with the way people work, which means that electricity needs to be going into the machine at the right time, at the right cost as well. If we look at working with electric machines, basically what we can see from experience is that there's quite a number of things that are changing compared to conventional machines. So the source of this image is the ENI, which stands for a network of construction companies that basically united to electrify heavy equipment in the Netherlands. And they joined as a group in order to share the lessons learned and together go a bit faster than when everybody would go at it on their own. So basically the elements that are changing on the site is there are now electric machines rather than the diesel ones. There's the introduction of charging infrastructure, which was not there before, maybe even energy logistics as to how you get the energy to the specific location. It has an impact on the design of the site itself, the construction site. It also has an impact on the planning that is being done. And potentially it also has an impact on the productivity of the people at the site. And then what we can also see is there's new rules and new disciplines that are being introduced in terms of worker safety, but also in terms of handling these types of equipment. And then in a general note, what we see is that specifically in the construction area, people are not very familiar with electricity, right? Folks have been a lot about doing the job and doing it with a machine that they understand. And now there's this whole new element that comes into play. So a lot is changing. And if we translate this into what that means from a total cost of ownership perspective, we come to the next picture. So basically what this shows is there's different types of cost involved in operating electric machinery. The first one is basically, the machine being too expensive from the previous poll. So it's driven by design choices. Which components do I select? What do I put in there? And that determines how expensive the machine is to purchase. The second part is very much focused on operating the machine. So how much energy do I need? how am I going to get the energy into the machine, and what does it mean for my productivity? And then there's a third element that we've seen here in practice in Europe, and that has to do with general cost. So this can be maintenance cost, but what we've also seen is insurance cost. And insurance costs somehow are related back to the design choices, where a more expensive machine can also mean that the insurance costs actually go up. Now, maybe diving a little bit deeper into it. So when we look at the design choices, clearly, the machine has a cost, but also what we call the drivetrain has a large cost. And specifically, the battery is one of the largest cost components when moving to an electric version of the machine. When we look at the energy, at the cost related to using the machine, there's an area which is interacting with the machine design, right? Which has a lot to do around energy efficiency. A not so efficient drivetrain means that you are going to consume a lot of kilowatt hours during the life of the machine, therefore making that element more expensive. It also may mean that the machine initially is a bit cheaper to buy. What we also see is that basically the efficiency of the machine will impact then your charging infrastructure and potentially also your energy logistics and your productivity. So there's a number of factors that are interwoven here and that impact each other and that are not as easy as a rule of thumb to resolve. Therefore, what we would like to point out is that the TCO composition actually depends on the type of machine and the type of work that you do with the specific machine. Now, this is quite theoretical, and this is a general introduction. Let's see it as that. And now we'll dive a little bit more into at least the first part, so driven by the design choices. What does that mean? Well, if you start using data to design a machine, there's a number of things that actually fit together, right? So let's start on the right-hand side. In the end, we want a powertrain design that works for the job. And in order to do that, there's two very important elements. One is the price of the components that will determine the cost of the machine. And the second part is technical feasibility, which is basically saying, can the machine do what it should be doing? Now, in order to get there, to get to the right design, we start by looking at the use case, collecting data from the machine in the field doing the job it should be doing. Will tell you how the engine and the components are being used, and that will help in finding the right components to electrify. From there, by looking at that use case, you can determine the right components. You can set up basically a machine architecture, telling you which components can be electrified, which steps you want to electrify, how you want to do it. Maybe you want to not go for a battery, maybe you want to go for a hydrogen fuel cell or different ways. So that's then defined in the machine architecture. And last but not least, specific components, of course, have multiple potential suppliers. So the actual specifications of each of these components that would fit that specific architecture also need to be taken into consideration. If you combine all of this in modeling and simulation, and from there you can tick the box in terms of technical feasibility, and you can get a very good overview in terms of the component pricing, so the total cost of building the machine, and you also get a view on the efficiency of the machine. So let's take that into a very practical example. In this case, we are looking at a press-in machine, which is a machine that can be used for foundational activities. And what you see here is that there are three different functions that the machine does, and you can see them on the right-hand side. So we have a hydraulic drill motor that's basically drilling into the ground. We have a press motor, which is pushing the foundational material into the ground. And then we have tracks, because most of these machines actually are self-propelled and need to move from one location to another. Now, when we look at the architecture, in this case, looking at use case data, or at the design, I should say, of the machine, a first option is to electrify the first part and keep the hydraulics the same way as it is today, which means that you've got the tracks on hydraulics, you've got the press on hydraulics, and you've got the drilling functionality on hydraulics. The hydraulic pump in this scenario will be powered by an e-motor with an inverter connected to a battery. If we then look at the second option that's available, that will be to take the drill functionality and directly connect that to the battery and have a separate e-motor for this function and to drive this aspect. And then there's a third option. The third option would be to also do the press functionality and connect that to the battery as well. What you see here is by removing these elements from the hydraulic pump, the requirements on the hydraulic pump may change as well. One could argue there's also a fourth possibility, which is also to replace the track motor and do that part electric as well. However, this machine, in this case, also has some other functionalities that are using the hydraulics, some minor functions, which means that there will always be a hydraulic pump required in the current design. And if we look at the use case, the machine is not often being transported. So adding a lot of complexity in the design to also electrify the track motor would not weigh up against the benefits you get from this. So that's in terms of how you can look at the setup. Now let's look a little bit more at the data. So we then start plotting the use case data. As you can see here, that's about pressures, that's about speed, it will be about RPMs of the engine, basically collecting the field data, which shows these little spiky patterns there that you can see there in the graphs. That will help you to understand what the machine actually is doing and how each of the parts is being used and how much energy each of the components is using in various situations. Once you know that, then the data collection on potential components start and also the energy consumption that goes along with that. So from there, we can simulate, right? So we can put the three potential architectures that we just described. We can put them in a simulation tool and we can look at what it means in terms of how the engine is performing, use case versus design. We can look at the torques that come along with the power losses, the temperature development that will be there in the engine, and basically run simulations to say, if you actually electrify this drivetrain to this type of setup with these type of components, then you're looking at this type of picture. Understanding whether that fits the envelope is basically passing the bar of will the machine functionally be able to do what it needs to be doing. These results can then be taken and translated into a cost overview. So now we're bringing it back to the total cost of ownership. Looking at that, we know what cost we are going to have in terms of electric motors, in terms of other components, in terms of the battery. And we also know the efficiency of the machine. And therefore, we know how much energy the machine will be consuming over its lifetime. Of course, we have to make some assumptions in terms of the energy cost, and they may vary from region to region, but it will help guide the decision-making in the process. So on the left-hand side, you can see the base architecture, which is basically the electrification just of the single functionality that we had in there. If we compare that with the cost overview of also electrifying the drill motor, then what we can see here is what happens is the machine becomes a lot more energy efficient. So looking at the green bar, you can see that this is now 31% lower than the first scenario, meaning over the lifetime, the machine will basically consume 1/3 less energy. That does come at a cost. So there will be another motor, there will be another inverter, there will be a lot more cables in the machine and a lot more connectors. And basically what you can see here is the gray and the bluish area, that they are going up, and quite significantly as well. But then we're going down to the next item, which is the size of the battery required to work a full day. And what we can see here is because of the increased efficiency, the battery sizing can be about 1/4 smaller than in the original scenario, which helps to drive down not only the initial investment for the machine, but also the total cost of ownership over the lifetime of the machine. And this is a key element, because looking at the first scenario, that may be the easiest way of electrifying and to get your customers an electric machine that does a job. However, the second one is the better option in this case. It may require a little bit of additional work in terms of designing the machine and developing the machine, but the benefits are twofold. First of all, lower cost in purchase price. Second, a more efficient machine, lowering the cost in operation. If we then have a look at the third scenario, so also electrifying the press motor, what we can see is the machine will become more energy efficient again. However, this time it's only 7% compared to the previous case. We do see additional components coming in, adding again a bit of cost. And then we see that the impact on the battery overall is relatively minor. So the saving on the battery is not sufficient to actually offset the additional cost on the motor and other components. Therefore, your total cost of ownership, but also your initial investment cost, is going up. So this actually proves that the third option is not the right option in terms of developing the machine and the way to go. So that was very much focused on how to design a machine on the basis of data. The next part was around energy use of the machine, so during the lifetime. So let's dive a little bit more into that part. So first part about being able to deal with additional costs of operating an electric machine is understanding how the machine is being used in practice. What you can see here on the graph is basically 3 types of excavators that have been measured for basically a year, and it shows the distribution in terms of work hours per day. So what you can see is that these machines do not always make 8 hours or 10 hours a day, but sometimes they are used very little, and sometimes they are used for a very long period of time. That is important to understand when you design a machine. So what am I actually designing it for? Am I designing it for people to always work more than 10 hours? Then the solution might actually be quite expensive for the cases where you only use it 3 to 4 hours. And vice versa. If you just design it for 3 to 4 hours, it will have an impact on when you want to use it more than 10 hours. Another element to look at is then not only the amount of hours that these machines are being used, but also the energy consumption when they are working. And again, if you explain that and look at that on a daily basis, you can compare different machines by looking at how much energy they consume compared to the size of the battery that's in the machine, which is the graph that you can see here, where 100% actually means that the amount of energy used by the machine on that day is exactly equal to the size of the battery. If you go over that, it means that you have to charge during the day, otherwise there's no way that you can complete the work that day. Again, we see here a very wide spread of situations different types of machines are using different amounts of energy, but also in relation to the size of the battery within the machine. So that's another factor to take into account when you design a machine, because what does this mean? Should I make it possible to do fast charging? Should I invest in that possibility and functionality of the machine? Should I maybe go towards swappable batteries so that I can swap out a battery and continue working? Those are key engineering decisions to be taken, and they will impact ultimately the cost, but also the model in which you operate the machine. Of course, seasonality also plays a factor in all of this. So we all know that in winter times, energy consumption is higher than in summer times. And being able to quantify that will also help you understand implications in terms of machine design. What we see in this case is for two different types of excavators, we can see that it can be plus 17.5% in winter months compared to the annual average, and almost minus 20 in the summer months. So that's a key factor to take into account. And primarily, this can be correlated with the temperature, of course, where we can see that the dip in the temperature basically means that you will start consuming a lot more energy and vice versa. And then there's, of course, the activity, because a lot of the off-highway machinery is not developed to do just one thing. It's actually to get a job done for which the machine needs to be able to do multiple things. If you think about an excavator, the excavator typically can pick up stuff, can drive it around, can reorganize it, can dig, but it can also do profiling, for example. Looking at the CAN bus data from the machine and analyzing that will allow you to determine the activities that are taking place and to then display these in terms of how much energy is being consumed per activity, but also how much time is being spent on each of the activities. Understanding this part can later on help in terms of predicting the energy that you are going to consume to complete specific activities. Now, I want to take you into an example of this. So Unitial has been working with our local community here in terms of doing a pilot project together with a large construction company on a zero-emission urban construction site where the job was to replace asphalt and the sewer over a stretch of a couple of 100 meters of the street. And this was to be done completely with zero-emission machinery. So when we look at that, let me just walk you through the pictures, top to bottom, left to right. So the first part that we see is the fenced off area, including at the back end, you see there a charging frame, you see a mobile crane, and you see the end of an electric trailer with a crane on top. Second picture is then the power distribution box with some AC and some DC connections attached to it. The third part is a battery charging frame for swappable batteries that go on the back of some of the less mobile cranes. And then the fourth picture, top right, that you see there is a mobile crane, 16 tons, charging locally at just a public 11 kilowatt charging station. The bottom left picture is the setup of the same location, but then with a buffer battery that is there, a small one. And the buffer battery basically allows to pull energy from the net, from the grid during the day, and to use that at night to have a little bit more energy available to charge the machines and to keep the operations going. Then what we're looking at is a switch to change day and night settings in terms of how the electronics are set up. And then there's a picture of a vibration damper, and last but not least, some smaller wheel loader, electric as well. So quite a lot of equipment over there. And of course, in order to be able to do such a project, it's important to forecast how much energy you are going to need. And from there, to be able to arrange that that energy is also going to be there when the work is being done. So let's start with creating a profile that looks at the time and at the work that is to be done, and then looks at how much energy needs to be charged. Of course, from there, you can look at the amount of available hours that you have for charging, and from there, you can determine how fast the charging needs to happen. So this is a bit of a puzzle that needs to be put together in terms of preparing for zero-emission works so that the energy supply and the energy demand in the end match. What we've done on this project is we've started measuring all these pieces of equipment to see what's happening in real life. And what we could see is that the real machine data is showing lower consumption. Now, why is that the case? Very often, what happens is in the prediction and in the forecasting, it is assumed that every day the machine needs to be able to do everything, specifically the most heavy work. However, when we look at the real use case data, the real data collected at that location, what we could see is that the machine is driving a bit, and it stops. Then it swings, then it digs, then it stops. Because other things and other activities need to happen at the job site. So the actual profile is not one of continuous full power, but actually one where there's a lot of peaks and troughs in the energy consumption and the use of the machine during the day. And of course, when you start planning for a production, for a construction site and for the charging facilities at that site, then this really matters, because how much energy do I need to get to that site? And the amount of energy you need to get there may actually determine the options you have. Do you need to get batteries there because there's simply not enough grid connection available to get all the energy? What kind of chargers do I need? Do I need to do fast charging? Do I need to have some fast charging stations around the corner where the machine can charge during the lunchtime? That's going to matter because it's all additional cost in terms of operating the machine. So if I then bring all of that back to a conclusion, then basically what we can see is that data can be used to improve the total cost of ownership of an electric machine. And that can be done both in the design phase, where it can lower the overall cost by balancing various components and setups and machine efficiency, basically because there's a major cost driver in terms of the battery. And then in the actual use of the machine, there's also this case to be made to use that data to optimize and to forecast and to look at how much energy am I going to need with all this electric machinery, and how can I match that with the available energy, the logistics of this, the charging, and also potentially energy contracts to save some money there. So I wanted to conclude with a call to all OEMs, and that is to share the data and/or standardize machine messages to really advance the future of electrification. And with that, I've come to the end of this presentation.
All right. Thank you very much, Marc. That was a very, very interesting presentation. We do have a few questions that have come in. So the first one from the audience here is, how do you perceive the impact of maintenance costs between electrified and non-electrified machines? And what factors do you believe contribute most to any differences?
Yeah. So what we see is that electric motors simply require less maintenance than traditional combustion engines. But that does not allow you to eliminate all maintenance on the machine. So some of the parts will require less maintenance. But what we see, for example, in the example that we showed, is if you maintain the hydraulics function, you still are going to have to do the maintenance on the filters, on the hoses in terms of making sure that they don't start leaking. So there will be elements where the switch to electric will lower the cost, but it's not a 0-1 game, right? So there will be remaining maintenance costs, mainly due to some parts not being replaced with a better option yet. So I think that in part answers the question. Can you just repeat it, Zach, so that I make sure that I've covered both angles?
Sure. It's kind of a 2 or maybe even 3-part question here, Marc. But the first part that I asked you previously is, how do you perceive the impact of the maintenance costs between the electrified and non-electrified machines? And what factors do you believe contribute most to any differences?
Yeah. So I think that actually then answers that one, right? So anything related to the engine, that will be replaced, because what we've seen in the field actually is that electric motors require hardly any maintenance. It's more related, so the remaining maintenance will be related to the parts that you're not replacing. Yeah.
Okay, and then the second part to that question is kind of a follow-up, Marc, is how do you predict the maintenance reduction from hydraulic to electric applications, right? What methods are you using to come up with that viewpoint?
Yeah. Well, I think that's a tricky one because there's so many factors that come into play when we talk about the cost of hydraulics, and also in terms of the possibilities that there are to replace them with electric options. I think in itself, replacing them with electrical parts nearly eliminates the maintenance element. However, the cost of these components can be a little bit higher, and sometimes specifically in terms of the functionality and the performance compared to the space claim, that tends to be more of an issue in terms of machine design.
Okay. Next question here is, you've talked a lot about the TCO, and your presentation was very enlightening, but it seems like maybe a bit of an end customer, an end user issue. So what would you say to OEMs and why they should be interested in this topic?
Yeah, I think that's a brilliant question, right? So when I worked at the battery manufacturer, I basically had the same view in the sense that I thought this is all about getting an electric version of the machine into the marketplace, and then the demand will kind of be there. And I think what we've seen is that simply is not the case. So the way that I look at this is OEMs need to help their end customers understand the TCO of operating an electric machine, because otherwise it will be fully dependent on regulations and basically people saying you can't use that machine in this area, which will be a very slow growth profile. And I don't think that necessarily is the right approach. So to give you an idea, what we see is smaller equipment. There actually the TCO is very positive because the energy cost of the machine go down, and that more than compensates for the fact that the machine is more expensive in purchase price. So in areas where the government is then starting to reward companies for being able to work cleaner, then these companies have a benefit that actually have these machines, right? So that's not really a subsidy, but that's more like a preference from the government saying, well, if we can choose, then actually we would like you to produce less noise. We would like you to produce less fumes, and we will actually give you a little bit of benefit in terms of rewarding the contract, because we don't just look at the raw cost, but we also look at the whole environment. And this is a movement that we can see in the larger cities. I think also New York pretty recently announced that it will be looking at noise reduction and basically cleaner air. And this is a movement we see very strongly in Europe. the main cities, but also in the Netherlands that we see as drivers, where you get some sort of a compensation for being able to do the job with less pollution than the other one. So if I then bring that back to the question, right? So to the end user, why should an OEM care about that part? If we want to make this transition, if we want to sell more electric machinery, it is important to understand that the end user needs to be able to profitably use the machine for the jobs that it's being contracted for. And therefore, he is going to need more help and more support, basically through data, we think, to be able to offer the right type of contract to the real end user, which is often a community or somebody asking for the works to be done.
Yeah, very good answer, Mark. Another one came in from the audience here. So beyond the powertrain, should the auxiliary hydraulic functions be electrified as well? And if yes, would this be more electric-driven hydraulics or electric replacing hydraulics?
That's a good question. And I don't want to be trying to wiggle my way out of it. But this is one where it really depends, right, on what makes sense. So what we've seen is that there's many cases where the OEMs choose not to change too much to a machine, but basically look at the impactful elements in order to be able to go faster and to keep the machine closer to recognition. I think what I've shown with the example of the 3 different setups is it's not always a case of the most efficient machine being the best solution. So what that actually demonstrated was that the additional cost of gaining a higher efficiency did not match up to the savings, right? And I think that is the true answer, right? So we will see in the future, I think, depending on the use cases, we will see different solutions being the right answer. Whether that's replacing the hydraulics fully, whether that's going to electric hydraulics, there's different ways to solve it for different machines. And I think that's the exciting part, right? In terms of applying the data and absorbing the complexity and coming back with insights as to what the right direction is.
Okay, that was a good answer as well. And then why can't we just get a machine that does the same as the diesel version? And I think what I'm maybe trying to ask is, there are certainly some differences between the two performance-wise. So what do you see as the reason we can't get a one-to-one comparison?
Yeah. So I've now been in this industry for almost 5 years, and what I've experienced from conventional machines is that the diesel engine was such a great technique that it never really mattered exactly what you did with the machine, because it could be designed to do everything. And if you ran out of fuel, it was very easy to top up again and to keep going. When we start looking more into the data, we can see that that is very inefficiently done. And because it's designed on maximum peak power to be able to do a lot of things at the same time. And I think when we start looking at the use cases, I'm not so sure you should be able to do everything at the same time, right? So this may actually be an area where some sort of a compromise. Sometimes it sounds like a big thing, but actually it's really minor in terms of not being able to drive and dig at the same time. I don't know, maybe a ridiculous example, right? But where you pull maximum power on different functionalities, maybe that's not the right way to go forward with electrification, because if you would do so, it will require massive, way oversized components, which will add so many costs that it's no longer interesting to do that machine. And I think by right sizing a bit more towards the actual use case, you can save a lot of cost, which will massively speed up the whole introduction of electric machinery.
Okay. And then maybe one final question here, Mark, and this will be from me personally to you. This is a very complex topic. You've gone through a lot here. So in order to help out the viewers and anybody that watches this later, you've done a lot of work on this. It's very clear. So what can you maybe give a one paragraph summary of kind of a best path forward that they can start on to assess their data and go down the path of this TCO analysis?
Yeah. I think that's a very good question, Zach. And I think if I would summarize it, I would say start really at the beginning, right? So it really starts with getting the data from your current process, from your current machine, whatever kind of jobs you do with that machine, and building the actual use case of what that machine is doing in the field. And that has to be the starting point. And often it is not, right? So that's what we've figured out, that often it's more theoretical use cases of scenarios that a machine should be able to go through. And I think the value lies in actually collecting the data from the real work that's being done. And that, for me, that will be the advice, all right, to start there, because that will give you a way better picture on what a machine should actually be capable to do.
Okay, very good. Marc, from all of us at the Future of Electrification conference, we want to say thank you for joining and taking us through this interesting topic.
Thank you for the platform.
I would say for everybody in the chat, you can see Marc's contact information here on the screen if you would like to reach out and ask him any questions. And with that, thank you very much.
Thank you.